Hi, chemistry class. I'm going to try to make this homework fairly short. This is chapter 6, and with most of its review, there'll be one or two things you'll learn in class, and we'll review them. They'll be brand new, but everything else we've really covered before, so we can get through it fairly quickly. Let's get started. This is called the electronic structure of the atoms. Although, even though it's atomic structure, I'm not going way back to Democritus or Aristotle. We get to pick up kind of with Bohr's model of the atom. So let's pretend Rutherford's done his thing. We know subatomic particles, and let's start with just where we're trying to find those electrons. So remember that we need to understand where the electrons are located by understanding the behavior of light. And so we're going to start off with the wave nature of light. Do you remember the measurements? Crest to crest, trough to trough, wavelength. And the number of waves that pass a given point per unit time is going to be frequency. All types of waves are on the electromagnetic spectrum, right? And they all travel at the speed of light. So here we have the speed of light, 3.0 times 10 to the 8 meters per second. And if we know the wavelength of light down here, do you remember that symbol? It's called the lambda. And if we know the wavelength of light, we know the speed of light, because that's a constant, we can actually calculate the frequency. What's that funny letter V? Do you remember that one as well? It's a nu. See if I can write that. N-U. Did I go too fast? I think you were supposed to write that back up there somewhere. So yes, frequency is nu, wavelength is lambda, and we can calculate the frequency because we know the speed of light is a constant. And again, everything on the electromagnetic spectrum travels at the speed of light. Back in, the 1800s or so, there were many scientists that were still perplexed because as you heated up metals, they would glow at different temperatures and different colors. And we didn't know why metals would glow. So it wasn't until Max Planck came along and he started looking at light and saying that, here's our analogy, if we walk up an escalator, we have a gradual, continual increase in potential energy going up the escalator. Very different than the stairs. So Max Planck said, what if we treat the nature of energy as not a continuous increase, but increments? Can you walk up a staircase on the vertical side? No. So if you pretend the stairs are quanta, little packets of energy, then they're very discrete intervals. Einstein showed this again, saying that maybe different frequency of light coming in can move electrons across different metals. Every metal has a different frequency where the actual electrons can move. There's a very lengthy video if you guys want to see it. But I'm not going there tonight or today. So point is, Planck's had discrete intervals of energy. And when we look at these, we can see that if we multiply the frequency by Planck's constant, then we have these intervals, Planck's constant nu, double Planck's constants, triple, on and on and on. Very discrete. How does this relate to the atom? Well, remember, we're trying to identify where the electrons are located. And so looking at light, how do we see the light? Bohr told us that in the 20th century, when we start to look at individual elements, they're not emitting continuous spectrums like the sun is. Remember, if we take the sun and we put it through a prism, we get all the colors of the rainbow. Bohr said that if we just look at a single element, whoops, sorry about that, we're going to get lines that are actually indicators of the wavelengths of light. So these are what we call bright line spectra, discrete wavelengths that Bohr observed. Each wavelength was an indicator of where Bohr said the electrons were probably located in the atom. It was at one interval or another, and not in between. So we came up with these places where the electrons might be located. He called those n's principal quantum numbers, but maybe they're located in one energy or the next energy or the next energy. He wasn't really sure, but he knew electrons couldn't be located in between. If you look at this diagram carefully, you see that there are some negative energy values. I wrote all over it, sorry. I think I've got another one there. There we go. And why are they negative? Because remember that electrons can absorb energy, and then how do we see the electrons? They fall back down and they release these photons of light of a very, very specific wavelength. And that's really telling us where the electrons might be located in the atom. So again, Bohr said the electrons can be allowed in one place, but not the other. So if we know the wavelength of light, then we can calculate the frequency, right? Because the speed of light is constant. So if we can calculate the frequency and we know these discrete intervals, we can multiply by Planck's constant to get energy. Do you remember doing this last year when we looked at the spectra? We can take it a step further here. Look at this big equation. A guy named Balmer and Rydberg came along and actually calculated the energy. This is Rydberg's constant. So you really can find out where the electrons might be located if we know the final and initial energies. What I want you to know is, looking at very specific wavelengths of light, can we get an indicator where the electrons might be located? And again, a little bit of review, but what do you think? If I'm going to fall from the second energy level to the first energy level, what's my light going to be? Violet or red? Is that going to be high in energy or low in energy? You guessed it. That's going to be the red light because it's closer to the nucleus. Those electrons that are closer to the nucleus are definitely lower in energy. Well, what was wrong with Bohr's model? It only worked for hydrogen. How many electrons are in hydrogen? Not too many. And it really was treating electrons like they followed Newton's laws of motion. And we know that they don't because they're very tiny particles. Remember that a charged particle moving in a circular path loses energy, so it would probably go crashing into the nucleus if we really used Bohr's model, is where the electrons might be located. But he did do some good things. So he said electrons exist in discrete energy levels. That's important. Energy is involved in the transition of an electron from one level to another. So remember, they jumped up, they exist in their ground state, they jump to the excited state, they lose energy, fall back down of specific wavelengths of light. You got that part right, and that was all good. But we have to take it a step further. So Louis de Broglie said, okay, we know that light can behave like quanta, according to Planck, but also like waves. And what if we have properties of both and assume that electrons can be treated with wave properties? Things with mass actually have wave properties. That's a new idea. So de Broglie came up with this equation. And he said, even if our mass is really small, then we can still calculate the wavelength of where it might be. Using this equation, let's bring that to classical mechanics or physics. What if I have a baseball and not an electron? If we did the math here, what do you think would happen? Let's say my baseball is moving at 95 miles per hour. A pretty good pitcher, huh? Does it generate matter waves? Meaning, can we see this? Could we see that wavelength of light? What's the mass of a baseball? Some of you guys should know. 145 grams, maybe? You do the math, and I bet you would find out you can't see it. The wavelengths would be so small that for tangible objects or visible objects, we'd never be able to see that object or that light. The wavelengths are way too small. So we'll keep it with electrons. We'll use de Broglie's de Broglie's equation for electrons only. Okay, so along comes Heisenberg, and he said, now wait a minute, how did we see those electrons? Didn't we have to put energy in so that the electrons jumped and fell back down? That's how we saw those electrons. We only saw light. But how do we measure that? You write this down. You may have to pause. But Heisenberg's uncertainty principle said the more precisely the momentum of the particle is known, the less precisely its position is known. Here's his equation. Again, what does that mean? You can't know one without the other. For electrons, we can't determine the location and the speed, because the harder we look at it, the more it moves. Ay. We'll never know. Very uncertain. Okay, so Schrödinger came along, and he developed this humongous equation for us, which was really important. And he said, you know, we can calculate the energy of where the electrons are probably located. And there you have it. Our wave equations gave us our wave mechanical model. And that's the really important part. This is our current model of the atom. And again, we did this a little bit last year. So here's his wave equation. And again, the most important thing is his wave equation allowed us to calculate the probability of finding an electron. We've got these electron cloud densities over here, and we can guess where they're likely to be. He called these orbitals. Where did those electrons exist? Now, we can take it a step further. This is brand new, so pay attention and try to follow along. So using his calculations, we know where the electrons might exist. And I know we did electron configurations last year, but now let's talk about some of those rules of where the electrons exist. Remember, they all have their own place. Every element on the periodic table has a different number of electrons. They're all in different energy levels. Bohr calls those energy levels N, the principal quantum number. That's our first quantum number. That's as far as we got last year. But let's take it a step further. As M becomes larger, the atom becomes larger, and the electrons move away from the nucleus. Oh, there's Miss Buchanan's little guy. So, looking at Bohr's model of the atom, I know this is not our wave mechanical model, but that's okay. We're going to use it anyway. So we've got 1, 2, 3. Very simply, our energy levels of the atom. Not too bad. Principal quantum numbers. But here's a new one. What about our angular momentum quantum number? Our quantum number depends on the value of n. So we've got a range here. What we're really doing is identifying the actual orbitals, or azimuthal number is what it's called, another name for it. So this is the shape. So quantum number L, not really a number, our letter L, identifies the shape. Let me flash this up here. This makes a little bit more sense. So all of our s orbitals have the L quantum of 0. And P is 1, D's are 2, and F 3. So we have the N number, our principal quantum number. We have our value of L for our second quantum number. Different orbitals, different shapes of the orbitals have different values. And M sub L depends on our L value. It ranges. Let me give you the examples down here. So if we're an s orbital, then we could have a magnetic quantum number of, this is a 3D number of 0. Why? Because there's one s orbital. Makes sense. 0. M sub L, how many p orbitals are there? There are 3 p orbitals. So we're going to say we can range from -1 to +1, identifying each of the p orbitals. Can you guess how many are in the d orbitals? Right? There are 5. And so our M sub L, our magnetic quantum number, is going to range from -2 to +2. These are the 5 orbitals. And then, of course, the F has 7 orbitals. So they're going to range -3, -2, -1, 0, 1, 2, 3. The range of all the orbitals. So here we go. I like this chart. We've got the N value, 1, 2, 3, 4, 5, 6, 7, because there are 7 energy levels. Our possible L values, we've got the S's are 0, the P's are 1s, the D's are 2s, and the F's would be 3, and that's as far as we've got. Not so bad, right? Our possible M sub L, these are identifying which orbitals they are. And then, got a vocab word there, electron shell. We've got one other to throw at you, though. Let's back up for a moment. So these s orbitals, little review here, are spherical. And as we get away from the nucleus, they get larger and larger and larger. And in the middle, we have nodes. There's Schrodinger's psi. At the node, we have 0. Here's a crazy thing. Put that up there. You can write it down. This is the node. Let me identify that. This is the node. And when the electrons are moving at the speed of light, right, they never hit the node. I didn't really emphasize this last year. But electrons can be found in this lobe, and they can be found over here. You will never, never find an electron at the very center. That's the node. It's magic. How does it get there? Electrons are crazy things. It's like they teleport from one lobe to another. Strange things, but that's what happens. You don't find them in the center. Here are your other orbitals. There are 5d and 7f orbitals. But you guys knew that, right? Those crazy shapes. They're the strangest looking paths of an electron. This is where the electrons are probably located and the energy that they have. Okay, remember these energy level diagrams for our electrons? We start at the bottom, we fill our electrons, and go away from the nucleus. Here's a new word for you, though. For a 1-electron hydrogen atom, orbitals on the same energy level have the same energy. Chemists call them degenerate. Doesn't mean they get in trouble a lot, but it just means they're all on the same level. So there we go. Degenerate electrons. They're all on the same level. Now, as electrons get bigger, then they're not. Electrons can be on all levels, of course. Here's our last quantum number, our m sub s number. This is the spin. Remember when we drew our orbital diagrams, we did up and down arrows? Because we're spinning in 2 directions, clockwise and counterclockwise. It's the only way 2 electrons can exist in an orbital. This is the Pauli exclusion principle, basically saying that every electron has its own address, its own place in an atom. There's the definition. No 2 electrons in the same atom have the same identical quantum numbers. So now you know the 4 quantum numbers. Electron configurations, you guys can do that. 1s2, 2s2, 2p6. Okay, we've got our orbital diagrams and our electron configurations. And there's nothing new here, so I'm not going to go over it a whole lot. We're still using big words, though. Hund's rule. Do you remember Hund's rule? For degenerative orbitals, the lowest energy is attained when the number of electrons with the same spin are maximized. What? That doesn't sound like review. Those are all new words. But you know what? We called it the empty bus seat rule, right? Nobody wants to share a seat with anybody else. So if we look, right, if there's an empty bus seat, you take it. All of these want to have the up spins. They all want to be spinning the same direction to maximize an energetically favorable position. That's all it means. That's Hund's rule. I just simplified it. Oh, look at this. We're almost done. So we've got the core electrons. We can do a condensed electron configuration just to show valence electrons. There's our beautiful periodic table written all out without the rare earth metals down below. So S, F, D, and P all written in a linear fashion. Kind of cool. Ooh, these anomalies are kind of weird, and we're going to talk about it definitely as we get into trends in the next chapter. One last thing in this chapter, photoelectron spectroscopy. That'll be fun. We'll get to that next time. And on to the periodic table. That's it. Short chapter. Bye, you guys.